Bismillahirrahmanirrahim. Assalamu alaikum. My name is Lefan Bajwa and I am from the Department of BS Chemistry and my ID is 007. Today from the course of Principles of Chemistry 3, the topic on which I am going to present my presentation is nuclear stability and radioactive decay. So before moving towards my presentation or starting my presentation, we should know one thing that the composition of the nucleus. So a nucleus is composed of protons, neutrons, and hundreds of atomic particles like hardons, muons, pions, leptons, etc. So nuclear stability. Nuclear stability means that the nucleus of an element is stable and thus it does not decay spontaneously emitting any kind of radioactivity. So a nucleus is said to be stable when it does not show the radioactivity phenomena. Among the approximately 9,000 nuclei expected to exist, the approximately 3,000 presently known, only 270 nuclei are stable against spontaneous decay, while the rest of them show the phenomena of radioactivity. Considering the pattern for the stability of nuclei, we can conclude that the nuclear stability is favored by even number of protons and neutrons. So the pattern of stability lies in the even number of protons and neutrons. There, as with all exceptions are always there. So there are only five stable nuclei known which have both an odd number of protons and odd number of neutrons. So odd nuclei, and these elements are nuclei are hydrogen, lithium, boron, nitrogen, and vanadium. So the next one is the magic number. The numbers like 2, 8, 20, 50, 82, 114, 126, and 184 are called magic numbers because if the nucleus is made up of nucleons that have the magic numbers, then the nuclei of such elements are said to be stable. For example, there are 10 isotopes of tin having atomic number 50. Having atomic number 50, that is proton number is 50. The most of any element, as we see that the tin is the example of the magic number, uh, but only two stable isotopes of its neighbor antimony having atomic number 51. So the pattern of stability lies in the even number of protons and neutrons, and that is the magic numbers. So when we plot all the elements according to their neutron to proton ratio in the graph, all the stable elements were obtained at the positions that make up the black line, which we call the line of stability, the zone of stability, the valley of stability. This one. So we can this here the neutron to proton ratio below the line of stability is 1, and above the line of stability it is 1.5 for lead, maximum value for lead. So we can predict the radioactive nature of any element in the graph or in the uh, periodic table. The elements above the line of stability, that is here, have greater number of neutrons, and so they will convert their neutron into proton. That is, they will have beta decay in order to get towards or come close towards the line of stability. So the elements below over the line of stability have greater number of new protons, so they will convert their protons into neutrons. That is, they will have beta plus or positron decay in order to come close to the line of stability. The elements lie here above the which have neutron to proton ratio greater than 1.5, where they will have alpha decay in order to get close to the line of stability. So the second part of my presentation is radioactive decay. Radioactivity is the phenomenon of the spontaneous disintegration of unstable atomic nuclei to form more energetically stable atomic nuclei. So when a nucleus is unstable, that it has a greater number of protons and neutrons, that is the neutron to proton ratio is greater than 1.5, then the element will have the phenomenon of radioactivity. Radioactive decay is a property of several naturally occurring elements as well as of artificially produced isotopes of the elements. So the radioactivity is the phenomenon shown by both natural and artificial radioisotopes. So and unstable nucleus will decompose spontaneously or decay into a more stable configuration, but will do so only in a few specific ways by emitting certain particles or certain forms of electromagnetic energy or radiation. So the radioactive decay process. The radioactivity have three types. The first one is the alpha decay. The second one is beta decay, which is further composed of or consists of positron decay and electron capture. And the third one is the gamma decay. So we will study or learn about them in the next slides. First of all, alpha decay. A nucleus emitting an alpha particle loses two protons and two neutrons. Therefore, the atomic number decreases by 2 and the neutron number decreases by 2. The mass number A decreases by 4. So when a particle undergo alpha decay, uh, undergo alpha decay, it will have its atomic mass less than 4, that atomic less than 4, and the atomic number decreased by 2. So here is the equation of the alpha decay, where X is the parent nuclei and Y is the daughter nuclei. Uh, the parent nuclei decays alpha particle or the and daughter nuclei have decreased atomic mass by 4 and atomic number by 2. The next one is the beta decay. When a radioactive nuclei undergoes beta decay, the daughter nucleus contains the same number of nucleons as the parent nucleus, but the atomic number is changed by 1. The equation of the beta decay is here, where X is the parent nuclei and Y is the daughter nuclei. When the X nuclei undergo beta decay and it has increased atomic number by 1, and it releases beta particles and antineutrino. Because A does not change, but atomic number changes, we conclude that in beta decay either a neutron changes to a proton or proton changes to neutron. So the number of proton has increased by 1 and the number of neutrons has decreased by 1. We can write the fundamental process of beta decay in terms of a neutron changes into a proton as follows. So basically the beta decay is the conversion of a neutron into proton, and the conversion of neutron releases beta particle and antineutrino. The next one is the positron decay. In beta plus decay, an energetic positron is created and emitted along with a neutrino, and the nucleus transforms to a daughter lower by 1 in atomic number and the same in mass number. The equation for the positron decay is written here, where X represents the parent nucleus, Y is the daughter nucleus in the excited state, and it has a decreased atomic number by 1, and it shows beta plus decay or positron decay with antineutrino is released. So the excited daughter nuclei further undergo gamma decay and becomes stable, or comes to the ground state. In positron decay, a proton changes into a neutron and positron and a neutrino. So basically, a positron decay is that in which a proton is decayed and converted into neutron, positron, and antineutrino. Here is an example of carbon 12, carbon 10, which shows beta positron decay or beta plus decay and converted into boron, releasing the antineutrino particle. So the next one is the electron capture, a process that competes with beta negative decay, and is electron capture, which occurs when a parent nuclei captures one of its own orbital electrons and emits a neutrino. The final product after decay is in a nucleus whose charge is decreased by 1. So The equation is written here where X is the parent nuclei that takes up the electron, its electron, and convert it into a product which has that is the daughter nuclei, which has decreased atomic number by one, and a neutrino is released in this process. In most cases, it is a K shell electron that is captured, and the process is therefore referred to as K capture. So here is an example of beryllium 47, which captures its electron, K electron. That is, this electron is captured by the beryllium nucleus, and it is converted into lithium, and a neutrino is released. At last, we will study the gamma decay, where a phononucleus that undergoes radioactivity is radioactive decay is left in an excited energy state. The nucleus can then undergo a second decay to a lower energy state, perhaps to the ground state, by emitting a high energy photon. So this is the equation for the gamma decay. The X represent the parent nuclei in the excited state, and after when it has gone through gamma decay, it comes to the ground state or lower energy state. So here is an example of the gamma decay in which cobalt convert show convert cobalt undergo beta decay and becomes excited daughter nuclei like nickel, and then the nickel loses or undergo gamma decay and becomes low and comes to on to the lower energy state. So when a nucleus decays by emitting a gamma ray, the only change in the nucleus is that it ends up in a lower energy state. So there are no changes in atomic number, proton number, neutron number, or nucleon number. So a nucleus may reach an excited state as the result of violent collision with another particle. More common, however, is for a nucleus to be in an excited state after it has undergone alpha or beta decay. So the following sequence of events represent a typical situation in which a gamma decay occurs. First of all, a boron element undergoes or through radioactivity, beta decay undergoes beta decay, and a carbon 12 in the excited state is produced as a daughter nuclei. So then the carbon in excited state undergo gamma decay or loses high energy photons and comes to the ground state. So this is the sequence for the radioactive decay of the like gamma decay. So this is all from my side. Thank you.